Welcome to the third part of our psychoacoustics lecture within the TU9 MOOC on communication acoustics. We're talking today about auditory frequency selectivity and critical bands, something absolutely fundamental and central to the auditory system and to processing of sounds in the auditory system as well as in signal processing approaches. In the past lecture, we've learned about auditory masking, and we heard that a tone can mask another tone. This is depicted again in this figure, which you already had in the other lecture. This figure shows the level of a tone necessary as a function of its frequency, so that this tone is just audible in the presence of another tone, which we call the masker. So imagine there's a masker of 1 kilohertz, 1000 hertz of various levels here, all the way up to 60 decibels SPL. And this masker is being played, it's masking another tone, and we vary the other tone's level so as to just hear the other tone, just be able to detect it in the presence of that masker. And this is what's being plotted in the masking pattern. And you already see that masking is most strongly near the masker tone's frequency, and masking decays to lower and higher frequencies. It decays much less, which we call the upward spread of masking, towards higher frequencies if the masker level is high, but it decays more strongly at low frequencies. We can now run this masking experiment and plot the data in a slightly different way. In this modification of the experiment, we keep the probe tone level fixed. So say we have a probe of 1 kilohertz and a fixed level, which is somewhere around here. And that probe now has to be masked. And we now vary the masker level so as to just mask that probe. And this is what's being plotted in the psychoacoustic tuning curve, which follows the idea of a physiological tuning curve. Now in the psychoacoustic tuning curve, it's exactly that masker level that's necessary to mask the probe of a certain level. And you see that this masker level increases the further away the masker is in frequency from the probe. So see here for a masker of about 500 hertz, a masker has to be 80 decibels to mask the probe at 1 kilohertz. And even more so if the masker is of a higher frequency, it will be very hard to mask a low frequency probe tone. And you see here that masking, the tuning curve increases sharply towards the higher frequencies. So this indicates a filter and a filter function in the auditory system. The masker is only relevant for masking the probe when it has a certain level, when energy from the masker falls into the filter that also holds the probe. This concept has been the concept of the energetic masking and giving rise to the critical band concept. Now there's one thing that we need to consider before understanding this, and that is our just noticeable difference in intensity. There is a certain threshold for us for detecting a change in intensity, and this is being depicted in this graph. So imagine an experiment where we change the intensity of a tone and we just ask somebody to hear whether the intensity changed or not between two successive tones, whether there is a difference between them or not. And we then vary the level difference between the tones as a function of their overall level to just detect that difference. And we call this the just noticeable difference in intensity, given here as a function of the sensation level of the tone. The sensation level is not the level in dB SPL, but something very closely. It's just the level relative to the threshold of hearing. So with 10 decibels sensation level, you'll be exactly 10 dB above the threshold of hearing. So if you're just above the threshold, then your sensitivity to level differences is still a bit poor, and the tone has to be changed by about 2 decibels to just notice that there's been a change in intensity. But in the main region of levels that we usually consider, from 30 to 70, 80 decibels, our sensitivity is about 1 decibel. So a change of 1 dB in intensity is just detectable. Changes below that we cannot hear, we cannot detect. And this gives the idea that masking at the output of an auditory filter will also be produced by a change in the probe's energy at the output of the filter that has to overcome this 1 dB threshold. And this gives rise now to the critical band concept. Now consider the auditory system to be composed of a bank of filters. And the auditory system looks at the output of the filters for changes in intensity or energy to make a decision whether a probe tone was heard or not. So our signal, the noise and the tone or any sound comes into the auditory system and is being filtered. At the output of the filter, we detect the energy. So the filter is being depicted in this graph with green dashed lines. Now, the tone is within that filter. The filter is always considered to be optimally placed for detecting the tone. Now, if we now play a masking noise that will mask that tone, then the auditory system can detect the presence of the tone only by an energetic change at the output of the filter that overcomes the energy of the noise. And we already heard that needs to be some 1 decibel increase at the output of the filter to just detect that there's been the tone present. We can now plot results, measure results of exactly that experiment. We can now take a noise that we increase in bandwidth, and if the noise has constant spectral density, so constant energy per hertz, then we will increase the energy of the noise overall. Now, with the increasing energy of the noise, with increasing bandwidth, we also need to turn up the energy of the tone to just detect it. And this is what you see in this graph here. The level of the tone relative to the spectrum level of the noise is a function of the noise's bandwidth. Now, if we raise the bandwidth of the noise, we have to also raise the tone. And you see this is a nice linear increase up to a certain bandwidth. And if you increase the bandwidth of the noise further, then the energy outside that filter does not contribute anymore to the masking of the tone. And this is the critical band. This is the idea of the critical band filter. And you see this here very nicely in the measured data for detecting the tone in noise. This is a so-called band widening experiment. And you can also see here clearly in this corner point, that's what we would estimate with this experiment as the critical bandwidth. Now, just in short, energy that does not fall in the filter, that's been filtered out, will not contribute to masking the tone in that filter, and hence it's not relevant for it. And you see this clearly here. You don't need to increase the tone's level further, even though the overall energy will increase further. Now, that's the critical band concept, and we can use this to estimate the critical bandwidth, but there are other experiments that are more widely used. Again, masking experiment, and the most widely used one is the noise experiment. So we turn the energy detection around. We have a tone that's of a fixed level, fixed frequency, and we have 2 flanking noises. And those noises are put together in frequency or further apart. And when they're further apart, the noise energy will not fall within the filter in which the probe tone is. So the probe tone can be detected easily. If the noise energy gets into the filter, so the noise separation is small, then of course we have to raise the tone's level to just detect it. And this is what's plotted here in this experiment. So on the left side of the graph, the noise separation is narrow, and we have to turn up the level of the tone to just detect it. And towards the right side, the separation gets further and further, and the tones level can be reduced. If we now fit two graphs to it, and you see this here in the dashed lines, then we see there is a corner point, and that corner point can be used as an estimate for the critical bandwidth. For this notched noise experiment, I also brought you a demonstration. We now keep a tone of 1 kHz of a fixed level, and we have a noise, two noises of 200 Hz bandwidth, and we vary the noise spacing so that when the noise is very narrow, it will to the tone, it will mask that tone. If the noise energy will fall outside the critical band, it will not mask the tone, so you can hear the tone. So we're not varying the tone level as it's plotted here in this graph, but we just change the spacing between them, and you will not hear the tone when the energy masks the tone, the noise energy masks the tone, and you will hear the tone when the noise energy falls outside the critical band. Now, we have all the ingredients and all the ways to measure the critical bandwidth. Let's first look at the critical bandwidth as defined by Zwicker, the Bark scale. Zwicker defined the Bark scale to be about 100 Hz wide at low frequencies and about 20% of the center frequency of your filter at high frequencies. High means here above 500 Hz. So at low frequency, he assumes about constant absolute bandwidth, and at high frequencies, he assumes about constant relative bandwidth. Note that this 20% of the center frequency is pretty close to what we have as third octave filters. These are about 23% of the mid frequency of the filter. A different definition is done in the equivalent rectangular bandwidth definition by Glassberg and Moore, different with respect to the bandwidth, particularly at low and at high frequency. So their bandwidth, here depicted in the blue curve, is much narrower at low frequencies, with its implication of longer filter ringing, for example, but higher specificity in the frequency domain, and more narrow at high frequency as well, compared to Zwicker. But again, the general idea is that at high frequencies, it's constantly relative to the frequency, because this additional constant here will not have much of an impact. Greenwood postulated the critical bandwidth from physiological measurements, and again here you have this constant that's added to a term from the frequency. And the Greenwood curve is plotted in green, and you see here that it's pretty close to Zwicker's bandwidth in the mid-frequency range, but again narrow at low frequencies and narrower at high frequencies. Knowing the bandwidth, we can now consider the auditory system as a bank of bandpass filters, and we can specify the width of the bandpass filters. These bandpass filters might well be overlapping, so the auditory system per se is more or less continuous. And these bandpass filters just filter for each frequency, for each auditory nerve fiber, a certain range of frequencies out of the sound. So we already heard the bandpass filters are narrow at low frequencies and they're wide at high frequencies in an absolute scale. This graph depicts the so-called gamma tone filters, which are very widely used when we consider the auditory system as a linear filter bank. And you can see here nicely that for low frequencies, here for 500 Hertz, where the filters are narrow, the ringing of the filter is very long. It can take several milliseconds for the filter to ring out after you excite it with a click. At high frequencies, the auditory system energy decays much more quickly, temporal resolution in a way is better, at least from the energetic point of view, because the ringing of the filters is much shorter. Also, when your filters are wider, and if you had a wide noise, then there will be more energy falling into the high frequency filters than into the low frequency filters. So for measurements, we often use 1/f noise or pink noise, which will then approximate to compensate for that increase in the bandwidth. So in short, using a range of bandpass filters that are more or less overlapping, and those bandpass filters have a width of 1 erb or 1 Bach, so basically 1 critical band wide, we can model the auditory system as a bank of bandpass filters. This brings us already to the summary of our short lecture on auditory frequency selectivity and critical bands. We've looked and learned that the auditory system behaves like a filter bank. We've seen the psychoacoustic tuning curves, which really look like a filter shape. A sensitivity for masking a tone is very high near the tone's frequency, but the masker needs to be turned up if it's further away in frequency than the tone. So there is a frequency selectivity, which really helps us also in processing sounds. This also is important for our loudness perception, as we will see in the next lecture. Linked with the critical band processing, filter banks, the auditory system has certain properties for phase processing. The sensitivity to phase changes across filters is limited, but if your components fall within the filter, then they're processed together and your phase sensitivity is fairly high. The critical bandwidth can be determined in a range of experiments, from loudness to masking experiments, and we find critical band filters that are narrow in absolute terms at low frequencies and fairly wide at high frequencies. The bandwidth, at least above about 500 Hertz, is roughly proportional to the center frequency, so it increases with center frequency, and using this knowledge of the bandwidth, we can now consider the auditory system as a filter bank with overlapping bandpass filters that are as wide as 1 critical band. That leads me to thanking you for your interest in this lecture and for giving you the hint that the next lecture will be considering loudness, where the critical band concept is of fundamental importance.